Hi, it's Tony Veroven, and I am here at the Irving, Texas 2024 NAFA Technical Seminar. And we're having a great time. And I wanted to take a little bit of time to record some podcast intros from the tech seminar from 2022. So this one is another great one. That year, we actually did quite a few or a little bit of extra content on sensing technology. You heard the episode with Dr. Jordan Clark from The Ohio State University, and this one is air quality monitoring sensor technologies for a data-driven future. So how do you know what's going on with your indoor air quality unless you are properly measuring it, right? So Zach Konway is our speaker of that day, and he's going to give you some great information. Enjoy.
You're listening to the Talking Air Filtration podcast, where you get to know the people that make air filtration possible and help us all breathe easier. Because clean air matters.
We'll get insights from air filtration professionals and learn how they became successful in their careers. Along the way, we will discuss best practices, guidelines, trends, and challenges in air filtration in a variety of applications. We hope HVAC, air filtration, and indoor air quality pros, including business development, engineering, building owners, and facilities management, will enjoy the insights our guests will bring to this podcast.
I'd like to introduce Zach Konway. He works for Kytera, a global leader in air quality and environmental monitoring, and has previously worked in water treatment and manufacturing. He has been involved in air quality monitoring for several years and has organized safety training sessions on chlorine gas for water treatment plant operators. Zach has a passion for human health and occupational health and safety and strives to stay on top of scientific developments in our current understanding of air pollutants. Please welcome Zach Konway.
Hi. So before I get started, I just wanted to quickly thank BGE Clean Air for introducing me to NAFA and NAFA for having me here today. I feel quite blessed to come from cold Canada down to warm Florida and had the opportunity to see the Tampa Bay Lightning win a game last night after they took the last two Stanley Cups from Canadians. So what I'm here to talk about today is air quality monitoring and specifically the sensor technologies that we have available to us and how we can leverage these technologies to improve the health, productivity, and safety of our built environments. So before I get started, I just wanted to quickly go over what I'm going to talk about in the session today. First, I'm going to discuss a quick introduction to indoor air quality. I'm going to talk about pollutants and the sensor technologies that we have available to measure each pollutant. I'm going to talk about how we can control viral transmission with indoor air quality. I'm going to talk about the benefits of continuous monitoring. And then I'm going to talk about some recaps and key takeaways, things that I really hope that you can bring forward when you're evaluating an indoor air quality monitoring company. And then I'm going to open up for a question and answer period at the end. So why measure indoor air quality? We have all kinds of standards as set by ASHRAE, and it was a pleasure listening to Bill earlier today. I suspect that some of the things I'm going to talk about, he was probably involved in the research after listening to him, which was really exciting. But the idea of measuring indoor air quality is that it will allow us to more quickly respond to issues facing the occupants of the space. It'll allow us to prevent occupants coming to us with complaints of sick building syndrome because we're able to ensure that we're providing clean air. So poor air quality is really the reason that we measure it, because then we can ensure that we're not putting our occupants in harm's way and having them breathing unhealthy air. So poor indoor air quality can cause a number of health implications. Oftentimes this can be referred to as sick building syndrome, but we can have health impacts such as headaches, fatigue, shortness of breath, stuffy nose, cough, asthma, and many other health impacts, both in short-term and long-term, depending on your level of exposure. Now, the idea of monitoring air quality isn't a new one. It's something that we started doing very early in the 20th century in coal mines. We used to use canaries as a way to determine when carbon monoxide levels or particulate matter levels were raising to hazardous for the occupants of the coal mine, the coal workers. The idea was it's much cheaper to replace a canary than it is to replace a coal miner. But it's 2021, and we have much better solutions today than we did in the early 1900s. We don't use canaries anymore. Now we use sensor technologies. We often talk about building clean and flush phases or coming in and doing performance testing. But this gives us a very limited snapshot of what is taking place in the built environment. If we are able to continuously monitor the air pollutants, we're able to know the true air quality. We're going to be able to address concerns before they even become concerns. We're going to be able to assess our ventilation and filtration to determine whether it's being effective at providing a healthy environment. And ultimately, we're going to be able to save energy without sacrificing the health and the comfort of the building occupants. Before I dive into actual pollutants and the sensors that we have available to measure them, there are a few things that I just want to quickly mention. The first of which is that the best way to ensure clean air is by removing pollutants at the source. If we're able to identify the source of a pollutant and remove it from a space, it's going to provide a far healthier environment. An example of this would be the removal of tetraethyl lead from gasoline in the United States, or the event of diesel exhaust fluid for diesel generators, or using clean building materials, not using building materials that had formaldehyde in the process, or not using asbestos as an insulator. When you're evaluating air quality sensors or any type of scientific equipment, it's important to understand how to calibrate the device. This is to ensure the accuracy and the precision and that you're reporting a good value. Now, many air quality monitoring companies will talk about software corrections, which is a little bit different than a calibration. A software correction can be effective at preventing drift of the sensor. A calibration, by definition, requires you to physically interact with the device, whether that is with a reference monitor or a reference gas, and correcting it to a known value. When you're considering air quality monitoring solutions, you should look at the entire cost of the device, not just the upfront cost, but also if there's going to be any operator costs. Is your facilities manager going to need to take the monitor to different spaces? How are you going to be installing it? Are there any subscription costs? How much is it going to cost to calibrate it? Are you going to need to replace it? Really try and do an entire life cycle analysis of the costs of implementing indoor air quality. And lastly, I want to tell people to dream big. Come up with big goals for projects when it comes to indoor air quality. If you have a specific idea of how you want the device to be deployed, or how it will tie in with an existing building management system for automation, dream big and find a monitoring solution that's going to fit the needs of your project. I don't have all the time in the world, so I'm a little bit limited on what pollutants I'm able to talk about today. But what I'm going to talk about is particulate matter, carbon dioxide, volatile organic compounds, also known as VOCs or TVOCs, radon, and ozone. First off, we're going to talk about probably everyone in this room's favorite topic, particulate matter, because the most effective way to remove particulate matter is through filtration. So particulate matter are solid or liquid particulates in the air, and what this means is they aren't gaseous. And we classify particulate matter based on its aerodynamic diameter, which is essentially saying that its propensity to stay airborne. And the larger particulate matter is going to come out of the air quicker, whereas smaller particulate matter is going to stay in the air longer. Now, there are many sources of particulate matter. We have dust, allergens, smoke, chemical reactions. And the reason that we should care about particulate matter is it's actually the most well-documented hazardous air pollutant. The particulate matter is one of the primary reasons that cigarette smoke causes cancer. But beyond just the health implications, the cancer, and the ability to pass through our lungs into our bloodstream, there are also productivity. So T. Chang had done a study, and he found that a 1 microgram per cubic meter increase in particulate matter concentration actually corresponds to a 0.6% drop in productivity. Now, I know this doesn't seem like a whole lot, but when you consider that generally guidelines, the US EPA defines good air quality as 12 micrograms per cubic meter or less, and most green building certifications are asking for 10 micrograms per cubic meter or less, you're essentially saying, we're okay with a 6% loss in productivity. That's still good, which I think is a pretty major drop when you think about it that way. When it comes to particulate matter sensors and the technology that we have available to measure particulate matter, there are really three options that we have. The first of which is infrared, which looks at the transparency of the air, and it's able to assign a level of particulate matter based on this transparency. It's really cheap. It's able to do continuous monitoring. The issue with infrared sensors is that there's no differentiation on particle size. It doesn't tell you if it's particulate matter 10 or particulate matter 2.5. Light scattering technology, on the other hand, uses a laser, and as particles pass through, it counts them. And how that laser diffracts when it interacts with the particulate allows us to bin the particulate matter into PM2.5, PM10, sometimes PM1. The limitation with the light scattering technology is that it's not able to measure particulates smaller than the wavelength of light used in the laser. In most cases, this is right around 0.3 microns. If you have a particle that has a physical diameter of less than 0.3 microns, it's not going to actually be able to be measured with the light scattering sensor in most cases. On the very technical, scientific end, we have the beta attenuation mass monitor. If you have $50,000 to $100,000 to drop on a monitor and you can pay an analytical chemist to run it, great. Oftentimes, this isn't the right solution for a building. It might be a great solution to take a sample and send it off to a lab for analysis, but it's not something that you would typically see for continuous monitoring. The next pollutant I want to talk about is carbon dioxide. And obviously, we're talking about it in terms of the built environment and elevated levels as humans occupy and exhale CO2 with every breath. We're not talking about CO2 as a greenhouse gas. And the reason we should care about carbon dioxide is lower ventilation rates can transfer to lower productivity. It can make the air feel stuffy, and it can cause us feeling like we're in a bit of a brain fog. And there actually has been a lot of studies on how CO2 can impact our productivity. So like Bill, I'm going to be quoting Joseph Allen quite a bit because that Healthy Buildings book is great. I highly recommend that you read it. So for every 400 parts per million increase in CO2, he actually found that our cognitive function scores drop around 21%. I think all of us can think of one time in our life where if we performed 21% better on an exam, we would have passed or been happy with our result. So it's kind of interesting to think that the built environment can provide this increase in cognitive function score. Even more than this, Joseph Allen found that cognitive function scores were 61% higher on days where the spaces were better ventilated. This essentially means that we were 1,200 parts per million above the ideal level on average, because we're 3 times that 21% value. You might be asking yourself, how much is that worth? How much money would I gain by improving the air quality and providing an environment that optimized the cognitive performance of the occupants of the space? Well, using data from the Department of Labor, he found out that that loss in cognitive performance averages about $6,500 per person per employee. And if we were to increase our ventilation with a typical system, the cost to regain that $6,500 is only about $40. And if you have an energy efficient system, that can come down to as low as $1. So that's an insane return on investment when you look at it in this way. There are 2 ways that we typically can measure carbon dioxide, and the first of which is electrochemical. It's really cheap, but the issue is that it's not very accurate. It's really hard to calibrate, and you're eventually going to need to replace it. And the reason for this is that it's a reversible chemical reaction. It is reacting with the carbon dioxide in the air to provide a change in conductivity. And if you think of it like your phone battery doesn't hold the charge that it did when you bought your phone. So in much the same way, the electrochemical sensor is going to lose efficacy with time. On the other hand, we have non-dispersive infrared. A non-dispersive infrared sensor is still relatively cost-effective, but it's a bit more pricey than the electrochemical. The benefit of the NDIR sensor is that it's a physical sensor. It has a much longer lifespan. You don't have that issue of degradation, and it's much easier to calibrate. One comment that I would make is water also absorbs a ton of infrared light. So if you see a CO2 sensor that doesn't have a humidity reading, it's almost always going to be electrochemical. So something I'm really passionate about is VOCs, or volatile organic compounds, which is essentially any chemical containing carbon that has a boiling point of less than 482 degrees Fahrenheit. So essentially what this means is these are chemicals that have the ability to evaporate, to off-gas and enter a gaseous state. They can commonly enter a space through building materials such as paints, adhesives, or carpets, but they can also enter the space from things like cleaning agents, or cooking, or body odors. And not all VOCs are harmful. Some are very harmful, like formaldehyde or benzene. Some are much less harmful, like propylene glycol or ethanol or rubbing alcohol. So it's important to consider both what VOCs are in the space and how you're going to measure them.
Are your air filtration personnel NAFA certified? Ask if they belong to NAFA and have their certified air filter specialist or NAFA certified technician designations. The CAFS and NCT designations are earned after rigorous exams and demonstrate that the air filtration professional has a high degree of knowledge and professionalism. To learn more about NAFA certifications, visit nafahq.org.
But even for the VOCs that aren't highly toxic, there's a huge impact on our cognitive function scores. So, like I said, I love quoting Joseph Allen. So in his book, he also found that a 500 microgram per cubic meter increase of VOC concentration is going to lead to about a 13% decrease in your cognitive function scores. So this is also highly tied to the CO2 level. So if you're properly ventilating and you're able to ensure that you're not losing this cognitive function, you're going to be able to ensure that your employees aren't losing that $6,500 per year. When it comes to measuring VOCs, there's really three ways we can go about it. The first of which is the metal oxide semiconductor. This is a fairly cheap sensor, and it allows us to continuously monitor VOCs in the space. It does have its limitations. It has poor selectivity, and what I mean by that is I would probably not recommend a MOS sensor to test for specifically formaldehyde, because it's going to have a difficult time telling if that's actually formaldehyde or if it's something much less harmful like propylene glycol or isopropyl alcohol. Its benefit is that you can do the continuous monitoring and you can then identify trends. Say you bring in new building materials and you're not sure of the source. You can say, okay, it's off-gassing during the evening. Let's bring in an industrial hygienist with a photoionization detector. And a photoionization detector is great because it allows you to have better selectivity. It can give a reading for specifically benzene or specifically formaldehyde. But it requires much higher power, and generally you need to have a trained operator in order to use a PID device. And it will need regular calibration with the reference gas or a reference monitor. Now, if you're sending things off to a chemistry lab for analysis or you're working in a university, you probably have access to a mass spec, either with gas chromatography or flame ionization detection. We're not going to talk too much about this because it's $100,000+ and not something you'd see in a built environment. The next pollutant that I want to talk about is radon. Now, radon is a naturally occurring, colorless, odorless, noble gas. So what this means is we have a very difficult time detecting radon with our senses. But radon is actually very harmful. It's estimated that radon is the #2 cause of lung cancer in the United States and globally, behind cigarette smoke. So the health implications are quite severe. Radon's formed by the decay of naturally occurring uranium and thorium in the ground. And if you look at the chain there, the uranium has a half-life of hundreds of thousands of years. Thorium has a half-life of tens of thousands of years. So what this means is that naturally occurring uranium and thorium isn't going anywhere anytime soon. It's going to be continuously decaying into radon. And radon is so hazardous because it's gaseous and we can breathe it in, and its half-life of 3.5 days means that it's actually pretty likely that it's going to decay in our lungs. And our lungs are not equipped to deal with that alpha particle. We're able to control radon through engineering controls, such as sealing the basements, because where it's coming from, the naturally occurring elements in the ground, it's primarily a concern in basements or below-grade areas. And because it is really related to local geology, not every location is going to have radon as a concern. So I would highly recommend looking up a radon map of North America. And if you're in an area that is higher chances of having radon, I would recommend testing your lower levels for radon. And I don't sell test strips, but that's kind of the biggest takeaway I'd like to have today is if you've never done a radon test and you live in an area where radon is a concern, do a test strip. So a test strip is essentially a way that you put a test strip out, you leave it for 3 months, and then you send it off to a lab for analysis. Be very careful with these as it's really easy to invalidate the results. If you put your finger on it, you're going to ruin it, and you're going to need to wait another 3 months and buy another test strip to get your results. But it's a really good way to identify if your particular building has radon as a concern. And if it does, I would recommend looking at engineering controls combined with continuous monitoring with something like alpha spectrometry that allows you to continuously get an idea of radiation levels. That is because things like fracking or other construction developments or earthquakes can actually change the radon that is able to enter a space. So if you implement these engineering controls, you're able to ensure that you're not being exposed to too much of it. One thing that I find really interesting is that it's the only air pollutant I'm talking about today that's not measuring the concentration in parts per million or micrograms per cubic meter. It's actually measured in terms of radiation or becquerels per cubic meter or picocuries per liter. So the next one I want to talk about is ozone. And when we talk about ozone, many of us think, ozone's a good thing. We thought it was a great thing 20 years ago. We were using it as an air purification solution, and it wasn't a great idea. And the reason for that is that ozone is a highly oxidative chemical, and it can damage our cells and decrease lung function, aggravate asthma, and cause inflammation. It is different than the ozone that protects us from the harmful UV rays. So when we talk about the ozone hole, we're talking about the good ozone, the ozone in the stratosphere. But ozone in the troposphere, which is where we're living and breathing, is very harmful. Ozone can be formed in several ways, but the most common ways are either high voltage, so things like lightning storms can cause lots of ozone, or reactions of NOx or VOCs with UV light and oxygen. This means that we actually do have a fairly stable baseline of ozone, and it tends to peak in the mid-afternoon. And from what I've seen, every US city that I've traveled to so far in the conference string, ozone has actually been the primary pollutant for the US EPA. So it is present quite often. And if you continuously monitor, you can allow yourself to bring in air at the times of day where ozone levels are minimal, providing a healthier environment. Or you can alternatively showcase that, hey, my UV light isn't causing ozone, or my other air purification isn't causing ozone, as it is something that many people are starting to become more aware about the negative health impacts of. When you go to measure ozone, we have three main ways. We have electrochemical, metal oxide, semiconductor sensors, which, much like the VOC and the carbon dioxide sensors, are quite cheap, but they aren't super accurate, especially at low levels. They both have issues with cross-sensitivity, and you'll eventually need to replace them. So with the electrochemical sensors, it's cross-sensitive with NOx, and it's cross-sensitive with chlorine. This was actually a much bigger issue when I was working in water treatment and working with chlorine gas sensors, because the cross-sensitivity to NOx and ozone meant that sometimes it would provide a false positive for chlorine. But if you measure your NOx, you're actually able to correct for it and thusly provide a much more accurate reading. Similar with the metal oxide semiconductor, if you're measuring your VOCs, you can correct for the VOCs and provide a much more accurate reading. Ultraviolet is very similar to the NDIR technology for CO2 in that you take light, you're shining it through the air, and how much of that specific wavelength of light is absorbed allows you to get the concentration of the ozone. The benefit is it has long lifespan, it has high accuracy, but the limitation is that UV is a much shorter wavelength, so the power demand of a UV sensor for continuous monitoring is much higher than that of NDIR for CO2. So I don't think, it would be 2021 if I didn't at least address the elephant in the room of viral transmission. I get asked all the time, is there a good way to measure pathogens or viruses in the air continuously? And I haven't found anything that has convinced me that it is possible to continuously monitor for pathogens or viruses in the air. That being said, there is huge correlation between things like your relative humidity and the ability for viruses to be transmitted. Same thing with ventilation and CO2 levels. So if we're able to use the data that we can measure, that we know is very correlated to risk of transmission, things like humidity and CO2 levels and VOC levels and particulate matter levels, we can showcase that we are properly filtering, we're properly ventilating, and we're properly purifying and providing an environment that is going to be ideal to allow our occupants to remain safe and healthy. The idea is that you can take this data and you can gain actionable insight. This data has use to us. We can take the particulate matter readings and we can assess our HVAC filters' efficiency or effectiveness. We can showcase that we're removing particulates from the air and providing a healthier environment. I think back to the wildfires in northern Ontario earlier this summer, and I have just a standard little HEPA filter in my room, and the air quality was better in my house than it was outdoors, simply because I was filtering out the harmful particulates from the wildfire smoke. You can know how disinfectants and cleaners are impacting your air quality through TVOC readings. This allows us to better choose cleaning agents or building materials, or find things that tell us when to call in the industrial hygienist. Continuous monitoring of VOCs should be that canary in the coal mine that tells you it's time to take action, it's time to investigate this further. Because it's not going to tell you this has formaldehyde if you buy new furniture from China and now your VOCs are going up when the space is unoccupied. You should probably test for it. It allows you to keep track of your occupant density and your ventilation with CO2 levels. You're going to be able to ensure that you're minimizing the spread of viruses or the likelihood of the spread of viruses and pathogens by managing your relative humidity. You're going to be able to tell your tenants, we've tested for radon. We know radon isn't a concern. And if it is a concern, we're doing the right engineering controls to prevent it from causing any negative health impacts. And lastly, something that I'm very excited about is you can take these key air quality indicators and you can showcase them to tenants. You can brag about it. Many companies have spent a lot of money on improving their filter systems or improving their HVAC systems over the past 18 months. And you're able to actually demonstrate with data that your filtration upgrades, your ventilation upgrades are doing what is required to keep you safe, to keep you healthy, to keep you productive. And one comment that I thought was really interesting from a talk that I was at last week was that facilities managers can oftentimes have a bigger impact on human health than doctors. And the reason for that is we spend 90% of our time indoors. You are very much in control of the health of the occupants. So I'm really happy that I get to be a part of an industry that allows this solution. So for some key benchmarks, if possible, we try to keep particulate matter levels below 10 micrograms per cubic meter. Like I said earlier, the US EPA breakpoint is 12. Carbon dioxide should be kept as close to atmospheric as possible, but typically 800 parts per million is a really great benchmark to strive for. VOCs you should measure and control in occupied spaces. Typically for green building certifications, there are guidelines on an hourly average. And the reason for that is you're going to have events. You're going to have people smelling, body odors or perfumes or cooking things or cleaning. And I like to think VOCs are kind of the spice of life. You don't want to get rid of them entirely, but you want to manage them. You want to control the events, and you want to ventilate them out to ensure that we don't lose that productivity. Ozone, you should control and keep below 25 parts per billion. This might be a pipe dream at some parts of the day when atmospheric levels are above 50, but when possible, if you're able to bring in the air before the ozone levels are high, you may actually be able to provide a healthier environment that way. Radon, you should measure and keep below 100 becquerels per cubic meter. And relative humidity, if possible, we should keep between 40 and 60%. I hope everyone is comfortable going out and knowing the tough questions to ask your air quality monitoring companies to appropriately evaluate and choose the right partner for an air quality monitor. I want you to carefully consider what the goals are for the project and how those pollutants and how those goals might impact you. Are you looking to tie it in with a building management system and automate ventilation? Are you just trying to showcase that your cleaners aren't releasing a ton of VOCs in the air? So ask yourself what the goals are, and that should allow you to decide what gases you want to go out and measure. When you're looking at air quality monitors, you should ask, how is this device going to be calibrated? How is this device going to be deployed? Consider what's important to you, dream big, and really go out and find an air quality monitor that allows you to achieve those goals.
Thanks for listening to the Talking Air Filtration podcast, a production of the National Air Filtration Association. Clean air matters.